All right, so the two choices are that it is in NP and it is NP hard, so it is NP complete. For colorability is NP complete. And the reasons are, well, so this one's true. We can, in fact, quickly verify a certificate that lists the color assignments. We actually did that in general already earlier in the unit. So yeah, for colorability is definitely in NP. It's not necessarily in NP because the number of colors is bigger. Well, no, the first argument is the correct one. It's not necessarily NP hard because having 4 colors to work with makes things easier. That is kind of true. 4 colors does give you a little bit more slack, and there's things that you can 4 color that you can't 3 color. But this argument is less compelling than the next argument that says that it is NP hard, and the reason for that is because a solution to 4 colorability solves 3 colorability. So if you give me a graph and say, is this 3 colorable? And to help you out, I'll give you an algorithm for solving 4 colorability. All I need to do is add a node to that graph, connect that node to every other node in the graph. That means that that new node is going to have a different color than everything else in the graph. And now you say, okay, is this graph 4 colorable? And if it is 4 colorable, then the color for this newly added node will be different from all the other ones, so the rest of the graph has been 3 colored. So we've actually solved 3 colorability, and that's why knowing that 3 colorability is NP hard tells us 4 colorability is NP hard. And no, since any graph that is 3 colorable is 4 colorable, that's true. That doesn't make them equivalent because it would also have to go the other way. Every 4 colorable graph would also have to be 3 colorable, and that's just not true. So this is actually the proof that 4 colorability is NP complete.